Hi everyone. Now we are all going to learn about the instruction set architecture. An instruction set architecture is a part of an abstract model of a computer that defines how the CPU is controlled by the software. It acts as the interface between the hardware and the software. Memory locations and addresses. Memory locations consist of millions of storage cells. Each can store one bit of information, which can be 0 or 1. The memory is organized so that a group of n bits can be stored in a stored or retrieved in a single basic operation. Each group of n bit is referred to as a word of information, and the n is called as the word length. The memory of a computer can be schematically represented as in the following diagram. Modern computers have word lengths typically ranges from 16 to 64 bits. If the word length of the computer is 32 bits, a single word can store a 32-bit in a 4 ASCII encoded characters, each occupying 8 bits, as shown in this diagram. A unit of 8 bits is called a byte. Words can be generally represented in a format as 0 to 2 power k minus 1. Suppose we are using 2 bits means 0 to 2 power 2 minus 1, that is 0 to 3. If we are using 3 bits means 0 to 2 power 3 minus 1, which is 0 to 7. Like that it goes on and on. A memory can have up to 2 power k addressable locations. Byte addressability. There are three basic information or three basic quantities that related with the byte: a bit, byte, and a word. A bit, as we already know, it's a single bit. Byte, it consists of 8 bits. Word can ranges from 16 to 64 bits of information. So that is what is called as the byte addressability. Bytes can be generally represented in big endian or little endian format. So in big endian, here the lower byte addresses are used for more significant bytes or left-hand bytes of the word. For example, if you are noticing the left side diagram, here the value starts from 0 to higher from left side to the right side. So here the big endian mode, it always starts from the left side. Next is the little endian. It is used in the opposite ordering, where the lower bytes of addresses used for the less significant byte, that is the rightmost bytes of the word. So as we discussed, this is the example. The right side diagram is the example for little endian mode. Next is the word alignment. Here, in case of a 32-bit word, natural word boundaries occur at addresses 0, 4, 8, and goes on and on. For practical reasons associated with the manipulating binary coded addresses, the number of bytes in a word is a power of 2. Hence, if the word length is 16, 2 bytes, aligned words begin at a byte addresses 0 to 4. And for a word length of 64, 23 bytes. Aligned words begin at byte addresses 0, 8, 16 and goes on and on. Words are said to have underlined addresses. Accessing numbers and characters. A number usually occupies one word and can be accessed in a memory by specifying its word address. Similarly, individual characters can be accessed by their byte address. Memory operations. Both programming instructions and data operands are stored in the memory. Operands and results must also be moved between the memory and the processor. There are two basic operations involving in memory are needed: read and write. In read operation, to start a read operation, the processor sends the address of the desired location to the memory and requests that its contents be read. The memory reads the data stored at the address and sends them to the processor. In write operation, transfers an item of information from the processor to a specific memory location, overwriting the former contents of the location. To initiate the write operation, the processor sends the addresses of the desired location in the memory together with the data to be written into a location. The memory that uses the address and the data to perform the write. Instruction and instruction sequencing. Here there are four types of operation that are performed in this instruction sequencing. First one is data transfers between the memory and the processor registers, arithmetic and logic operation on data, program sequencing and control, and I/O transfers. First, we'll discuss about the different types of notation. There are two different types of notation. One is the register transfer notation, and the another is the assembly language notation. So first, we'll see about the register transfer notation. In register transfer notation, here the address of the memory locations may be given in names LOC, place, A, VAR2, and on and on. The processor registers are normally ranges from R0 to R5. Registers in the I/O subsystem may be identified by their names, data in, or out status. In this example, you see how the data is transferred from the location LOC to the register R2. So another example, what we are performing is by using the registers alone. So here this is the example for register transfer. Here we are giving inputs to the registers R2 and R3, and we are sending the added value to the register R4. So this type of notation is the register transfer notation. And next is the assembly language notation. Here what will happen is load of R2, LOC means the indirect value of the indexed value of LOC is moved to the location R2. The generic instruction that causes the transfer described above from memory location LOC to processor register R2 is specified by the statement load R2, LOC. The second example of adding two numbers contained in processor registers R2 and R3 are placing their sum in R4 and can be specified by the assembly language statement. Add R4, R2, R3. That is, the value of R2 and R3 are added and they are moved to the location R4. An instruction specifies an operation to be performed and the operands involved. In the assembly language instruction, mnemonics are typically abbreviated of the words describing the operations. For example, load means it is LD and store means STR or ST. Next, we'll discuss about the RISC and CISC instructions. So RISC means reduced instruction set computer and CISC means complex instruction set computer. The restriction that each instruction must fit into a single word reduces the complexity and number of different types of instructions that may be included in the instruction set of a computer. Such computers are called reduced instruction set computers. A complex instruction set computer, CISC, is a computer architecture in which a single instruction can execute several low-level operations or and capable of multi-step operations or addressing modes within a single instruction. So here in this RISC, we have number of instructions, but we have a only simple instruction. But in complex instructions computer, which have a single instruction which will do multi-process. Next is the introduction to RISC instruction set. There are two key characteristics of instruction sets. Each instruction fits in a single word. Second is the a load store architecture is used. So that means generally we can use load or store to process the data. Load instruction format. So load is generally the format of load of destination comma source. So or we can use the processor register comma memory location. So next is the addition format. Here the statement C equal to A plus B. In high-level language program instructs the computer to add the current value of two variables A and B and to assign the sum to the third variable C. When the program containing the statement is compiled, the three variables A, B, C to distinct locations in the memory. For simplicity, we will refer to the address of these locations ABC. So in MIPS architecture or the ISA architecture, we can use the instead of values, we are using the locations. Here the ABC will be considered as the location. It is not the data. It is the location. To carry out this action, the contents of memory location A and B are fetched from the memory and transferred into the processor where their sum is computed. This result is then sent back to the memory and stored in location C. So we choose the registers R2, R3 and R4 to perform the task with 4 instructions. Load R2, A, load R3, B. The value of A will be moved to R2 and the value of B will be moved to R3, and then add of R4, R2, R3. It means the R2 and the R3 are added and their value is moved to the register R4. Then finally we store the value R4 to C. Here in this instruction set, the load instruction has the format of destination comma source and the store instruction has the format of source comma destination. So here we already seen that add is a 3 operand, add 3 address instruction form, add of destination comma source 1 comma source 2 and source of source comma destination. So this is how the instruction execution and sequencing will work. We assume that the word length is 32 bits and the memory is byte addressable. 4 instructions are in successive word location starting at location I. So since each instruction is 4 bytes long, the second, third and the fourth instructions are I plus 4, I plus 8 and I plus 12. Let us consider how this program is executed. The processor contains a register called a program counter, which holds the address of the current instruction to be executed. To begin the execution of the process, the address of the first instruction must be placed in the program counter. Then the processor control circuits use the information in the PC to fetch and execute the instruction one at a time in the order of increasing addresses. This is called straight line sequencing. Execution of the instruction. executing a given instruction in two-phase procedure. In the first phase is called instruction fetch, and the instruction is fetched from the memory location whose address is in program counter. This instruction is placed in the instruction register in the processor. At the start of the second phase called the instruction execute, the instruction in IR is examined to determine which operation is to be performed. The specified operation is then performed by the processor. So this is how the instruction set architecture, how we are working, what is the format, and what about the byte informations, and finally how we are executing the instruction. Thank you all for your valuable time. Thank you all.